Okay, having just talked about estimating a multiple regression model, I just wanted to circle back and talk about a few things in the simple linear regression model where the intuition is a little bit easier um, to appreciate. So I am building my analysis on an assumed model. So I'm assuming that I know what the population model is. It follows the simple linear regression assumptions and has an intercept parameter of 2000, a slope parameter of -4, and an error variance of 10,000. I'm assuming that the error terms are normally distributed with a mean of 0 and a standard deviation of 100, which is just the square root of the error variance. What I'm doing down here is generating a sample of 50 data points from this population. To do so, I have selected a series of 50 x values. The exact values there is not particularly important, but I generated them randomly from a uniform distribution, so they're evenly spread between 0 and 100. Then I randomly generated my error terms from a normal distribution with mean of 0 and standard deviation of 100. And then I used the simple regression model and those variables to derive y values. So if I double click on that, you'll see that y value is being calculated as 2000 plus -4 times the x value of 15 plus the error term. And that's being repeated for 50 more sets of observations. Some descriptive statistics are here. I'm not going to talk about them now, though. And here is some regression output that I've already generated. What I want to talk about in the remainder of this video is these parameter estimates and the standard deviation of these estimates, and then also an estimate of the error variance and the standard deviation, or the estimated standard deviation of the error term. So this is an estimate of the intercept coefficient. In my population model, I know that this is 2000, so it's fairly close to the true value. And this is an estimate derived, as this one was, using the least squares estimators. For the slope coefficient, its estimate is -3.65. The actual population value is -4, so it's in the general vicinity. And remember, my population model had an error variance of 10,000. The estimate from this model, this sample of data over here, is not dissimilar to that 10,000. And the standard deviation is, which in the population model was 100, is quite closely mirrored by the estimated standard deviation here of 97. I've drawn a graph of both the population model and the estimate derived from our sample of 50. So the blue line represents the population model. It has an intercept of 2000 and a slope of -4. And the red line represents our estimate of that population model using the sample of 50 that I randomly generated. It has an intercept of 1980 and a slope of -365, giving rise to this fitted model. Now, over here, I have shown the sampling distribution of the estimator B1. The estimator B1 is a statistic which is being used to derive estimates of the population parameter B1. So every time we draw a sample, we feed the x and y values from that sample into this formula, and it produces for us an estimate. In the sample that we looked at, my estimate was 1980, which is a little bit less than the true population value. If I took repeated samples, I would see approximately half of the estimates were above this population parameter, and approximately the other half would be a little bit below the population parameter, as we saw in my particular sample. These B1 estimates will be distributed in a probabilistic way, which is shown by this probability density function. It has both a mean, which is the population value of 2,000. Because its mean is the same as the population value, that means that this estimator B1 is unbiased, and its dispersion is measured by its standard error. So this is an estimate of the standard deviation of this distribution. The scale, incidentally, I'm not sure if I mentioned already, the scale here is identical to the scale here. When I look at the sampling distribution of the slope, which is I've depicted down here, the scale doesn't kind of map across quite so neatly, but I can say that if I just cut a line here and look at where the different lines are showing there, I could map that across to a scale, and it would give rise to a sampling distribution. So for this sampling distribution of B2, the estimator of the population parameter B2, it has an expected value that's equal to the population parameter of -4, but we will, because of sampling variation, we'll sometimes have estimates that are above the population parameter and sometimes below. In my sample of 50, it was a little bit below the true, I probably should say above. It's less negative than the true population value. This sampling distribution, as well as having this mean or expected value, has dispersion that's measured by its standard error, and in our sample we came up with an estimate of 0.47 for the standard deviation. And this standard error tells us how precise our estimate of B2 is likely to be. A smaller standard error means less dispersion in this sampling distribution, which means that our estimates should be closer to the true population parameter. The other thing that we saw in the regression output was something called the standard error of the regression, and I mentioned earlier that that is an estimate of the standard deviation of the error term. So let's just talk about that briefly. Let's say I selected a value of x of 40, and I wanted to look at the distribution of all the y values that were paired with x being 40. So I would find that on average those y values should be equal to this value of y, which is shown on the population, the blue line. But I wouldn't expect that every single y observation that I saw where x was equal to 40 would be equal to that value. Sometimes I'd see y values that were up here, sometimes values that were down here with negative error terms, positive ones being up here. But in general, they would be concentrated fairly close to this mean value, and as I got further away from that mean value, I'd expect the frequency of observations out there to be less and less. And because this model is homoscedastic, I could set up an identical probability density function for any value of x. So for example, I could draw one if x was equal to 80. Then I would find that my PDF should be centered over this expected value, and it would have dispersion that was the same as the kind of dispersion that we could see here. In fact, that's illustrated quite nicely in another worksheet that I've got over here. I'm running with the same population model as previously, but now I've generated a population of 10,000 elements, and they're shown by these grey dots in this scatter plot. And you can see the distribution of these scatter plots around the population model, which is shown with this black line, is fairly uniform. It's quite dense, just a little bit either side of the black line, and as we move further away from the black line, we find that these grey points are less and less frequent. And it's roughly the same in terms of the density of these values on both this side and this side. And whether I looked at x being equal to 30 or x being equal to 60, the distribution of grey points on either side of that line is pretty much identical. It's almost like you can see some parallel tracks running through here, and that the fact that these values are all roughly distributed the same distance either side of the population model tells us that we're dealing with a homoscedastic model here. Also shown on this diagram is an orange regression line, which is an estimate derived from a sample of 50 data points, which are these orange dots on the graph. And what you can see if you press F9 is Excel choosing a new sample and showing you the new regression line for that sample. So I'll do it a few times and watch how the orange line fluctuates around. In particular, look at how the estimate of the intercept changes. So I'll keep going. Estimate of the intercept is less than the true population value, less by even more, a little bit above, approximately equal to the population parameter, a bit above, below, a little bit above, slightly more above, and so on. Hours of fun can be derived from this, this little simulation. But what we should see over time is that the intercept term will tend to be concentrated, the estimate that is, around the true population value here. We'll see roughly half our observations of the intercept, or half our estimates of the intercept being above the population value, the other half below, with most in this kind of range and a few occasionally a bit more dispersed from the true population value. The same kind of thing would apply to the slope estimates as well. And what we're seeing is in fact sampling variation, which is depicted in that was unexpected, which is being depicted in this sampling distribution here. Okay, so just to quickly go back to our Excel model, we've talked about these being point estimates of parameters, that one too, and that these are showing the precision of these estimates. They're the standard deviations or estimated standard deviations for our estimates of the population values, and we also saw that that standard error represented the standard deviation of the error term in the model. Okay, so hopefully you've got a bit of a better understanding now of what those standard errors that you see in the model actually represent. I should point out that these standard errors are very important in the hypothesis test values that are being shown here, and also the two sets of confidence intervals that have been constructed out here. I'll save discussion of that for another video, however.